Here, we are to determine whether the given x vector is an eigenvector of a 2 by 2 matrix. We have 4 of them here, and we're going to verify them one by one using this given 2 by 2 matrix A, which contains 7, 2, 2, and 4. By the way, we have an important theorem which tells us that for any n by n matrix, the number of eigenvector is at most n. That would mean it's less than or equal to n. In this case, since it's a 2 by 2 matrix, out of these 4, we can show here at least 2, at most 2 of them to be identified as eigenvector of matrix A. For us to be able to identify which of these 4, we're going to examine all of these 4 in this manner. You have A, X, we have the product of your matrix A, and any of these x vectors must be equal to lambda x. Okay? And if there exists a specific lambda for a specific vector here, that would mean that is the eigenvector of together with its corresponding eigenvalue, the lambda, for this 2 by 2 matrix. So let's do it like this. Let's try to verify the vector on A. Our vector is at 1 and 2, so we're going to show here A, X. So let's have it thicker. Must be equal to, you have 7, 2, 2, and 4 to be multiplied with 1, 2. This is a 2 by 2 matrix. This is a 2 by 1 matrix. The result of this would be a 2 by 1 matrix as well. So let's do it in this process. 7 times 1 is 7. 2 times 2 is 4. 7 and 4, you will have here 11. Okay? Next, 2 times 1 is 2. 4 times 2 is actually 8. 2 plus 8, you will have here 10. This is the result of the product of your matrix A to be multiplied with the vector in your A vector. Now, if we are going to examine this, we must be able to express a certain lambda together with your vector x here. And if we could express it like this would mean that our x vector in A is an eigenvector of matrix A. However, take note that the vector that we have multiplied is 1 and 2. Using the first entry to make this 1, we can actually factor 11. However, if you're going to factor out 11, you have 1, and what happens to your 10 is actually 10 11ths as we factor out 11, because once you return multiplying that, you will lead to 11 and 10. So this is your eigenvalue. However, this should be your lambda, which is yet to be identified as eigenvalue. So we have that, but look at our matrix, vertex vector here. Sorry, look at our vector here. This is not similar to the vector in your A, which is 1 and 2. This is the indication that the vector x for letter A is not an eigenvector of matrix A, because it could only happen if once we take out a certain lambda, the remaining matrix here should return to the original vector as presented here. So let's continue with letter B. So you'll have A times x as well, but we're going to use now our second vector here. So your A is the same, 7, 2, 2, and 4 to be multiplied by 2 and 1. Same thing, a 2 by 2 matrix times 2 by 1 will result to 2 by 1. 7 times 2 is 14. 2 times 1 is 2. 14 plus 2, you will have here 16. Next, 2 times 2 is 4. 4 times 1 is 4. 4 plus 4, you will have 8. So from here, let's try to look at our vector here, and we should be able to express this into a certain lambda times our x, which is 2 and 1. And to do that, since we're talking about the second entry as 1, let's try to factor out 8. What happens to your matrix here is 16 divided by 8, you have 2, and you have here 1. This is a certain lambda that you were able to factor out, and look at this vector here. This corresponds to the vector in letter B. So this is our x. Unlike your letter A, to which this is not equal to your vector here, this is equal to the vector used. This would mean that the vector in B is an eigenvector of matrix A with the corresponding eigenvalue equal to 8. Okay, so just a note for that. Yes, together with its eigenvalue equal to 8. So we already have 1, and since again we expect to have less than or equal to 1, we might have another one of which, depending on which do we prefer here. So let's continue here at the bottom, our C. So again, we're going to verify this, and of course our A is the same. You will have 7, 2, 2, and 4. 7, 2, 2, and 4. And our vector for letter C is 1, negative 2. So you have here 1 and negative 2. So the product here, 7 times 1 is 7. 2 times negative 2 is negative 4. 7 minus 4, 3. Next, 2 times 1 is 2. 4 times negative 2 is negative 8. 2 minus 8 minus 6. Okay? Now look at our vector used. We have 1 for the first entry. So for this, let us try to factor out the scalar 3. And what happens to our matrix? We'll have 1 and negative 2. This is the certain lambda that we're able to remove with our matrix. And examining this is actually similar to the vector on letter C. In short, we have shown here that this is also an eigenvector of matrix A with lambda, the eigenvalue, equal to 3. We already have 2, and with this, again, we're only having less than or equal to n. So we might say that our vector D is no longer an eigenvector, but just for the purpose of the illustration, let's try to come up with the same process here. Is equal to 7, 2, 2, and 4 to be multiplied with your vector here, negative 1 and 0. Negative 1 is 0. So the product of this, 7 times negative 1 is negative 7. 2 times 0 is 0, negative 7. And then 2 times negative 1 is negative 2. 4 times 0 is 0, so you will have negative 2. But take note of what vector you applied here. It's negative 1 and 0. To reach this, you can simply factor out negative 7. Positive 7. Okay? Factor out positive 7 so that the first entry will still be negative 1. However, your second entry will not be 0, as this will become negative 2 over 7. This is our lambda. However, this doesn't fit our x vector for letter D, as this is not the same as the vector used here. As an indication, this is not an eigenvector of matrix A. As mentioned, we already have vector x or x vector in letter C and in letter B, which satisfies this, and this is how we determine whether the set of x vectors here, or which of them, is an eigenvector of a 2x2 matrix together with the corresponding eigenvalue. Thank you very much for watching.